Christian, thank you very much again for being here. It's really a pleasure to have you here. One of the first sessions of our weekly seminar. Thank you so much. Please.
Yeah, thanks a lot for the invitation. I'm happy to have been given the opportunity to present you our research. What I want to do in this seminar is to talk about our trapped ion experiments, where I first want to introduce some timescales and tools, and then try to explain you how we can make trapped ions interact with each other in an interesting way. And this is then a major tool for creating an artificially engineered quantum system with which we can then carry out quantum simulations. And towards the end, I want to discuss prospects for scaling up the system to large ion numbers. But let's first start maybe with a look into our lab, where you can see here that you see the optical tables, which host the lasers that we use for manipulating ions. And I think I have a pointer here. And you see here a vacuum system on the table, which houses the ion trap that we use for confining strings of ions or crystals of ions. And these are really the main two parts of our experiment. Lasers are very important for several reasons. We use lasers to create ions in the first place. We use them for laser cooling to very low temperatures, such that we can describe the ion motion in the confining potential of the ion trap as being quantized. Then most importantly, we use lasers for coherently exciting the ion, which is our tool for creating entanglement. And ion lasers also play a role for detection of the quantum state of an ion via fluorescence measurements. The ion trap, on the other hand, permits us to load strings of ions on a time scale of a few minutes, which is a short time compared to the storage time in these traps, which can be a day or even days. And this storage time, on the other hand, is very long compared to the typical duration of an individual experiment, which lasts maybe 20 milliseconds, and which is comprised of the initialization of the ions in a particular state, which involves laser cooling and optical pumping, the coherent interaction of the ion with a series of laser pulses, and then the quantum measurement. And the comparison of these timescales shows you that with such a system, we are able to carry out something between maybe 10 to the 5 to 10 to the 6 quantum measurements per day, which is a lot compared to maybe some other systems, which is not so much compared to systems like superconducting qubits, but it means that we have as a resource a fairly large number of copies of a quantum state that we can produce within a given time, and that we can then try to make use of in the best possible way. Now, in the traps that we use, we confine ions in potentials that are harmonic and anisotropic. And the typical trapping frequencies that are used for trapping strings of ions, like the one that you can see here, are on the order of a megahertz or a few megahertz. And this frequency is important because it sets one important length scale, and that is the distance between neighboring ions, which is typically on the order of a few micrometers. And this is a distance which is substantially bigger than the laser wavelength that we use for manipulating the ions, which by itself is bigger than the length scale to which we can localize ions when we ground state cool them, which is on the order of 10 nanometers. And then the smallest length scale I want to mention is a Bohr radius, which describes the atomic interactions at the level of a single ion. Now, why do I mention these length scales? You see that we have this separation of scales, which is important because you can see this first separation here enables us to spatially resolve the fluorescence of ions, as you can see here in these pictures. And this enables us to measure ions one by one, and not only by doing ensemble measurements of their quantum properties. Secondly, we are able to focus down a beam strongly such that it interacts only with a single ion in the string and not with its neighbors. So in this way, we can individually address ions, and if we encode a quantum bit in a single ion, then we can carry out single qubit manipulations that affect only that ion that we have chosen to interact with. And then finally, I would like to point out that the ion distance is many orders of magnitude bigger than the Bohr radius, which is good and bad at the same time. It's good if you consider your ions maybe as a quantum memory, if you want to store quantum information in a string of ions, because this tells you there are no state-dependent interactions between the ions. You don't have to worry that the quantum state of one ion is affected by the quantum state of another ion in the string. But on the other hand, it's bad if you want to engineer an interacting many-body system, because it means that you have to find another way of making the ions interact with each other in an interesting way. And yeah, before talking about this, let me mention that we use calcium ions as our ion of choice. Calcium has a simple level scheme with an S1/2 ground state, a short-lived P1/2 excited state, and a metastable state with a lifetime of about a second, which is interesting for encoding a qubit in conjunction with the ground state. And so you see that we can have here two levels which are nearly stable on the time scale of an experiment. We can use a very frequency stable laser to manipulate this qubit or this pseudospin system that we have here at our hands. And on the other hand, we can also carry out efficient quantum measurements of this qubit by using the transition to the short-lived level. The short-lived level cannot decay to the metastable state because of selection rules, and it can only decay back, and therefore we have here a closed transition on which we can scatter plenty of photons, and then this presents a way of projecting the qubit either into the fluorescing state, if it's the S1/2 state, and then we will see on the camera, for example, the image of a fluorescing ion. Whereas if it is projected into the D state, it does not couple to this laser here, and we won't see any light recorded in the camera. So in the pseudo-spin language, if you associate the spin down state with the S1/2 electronic level and spin up state with the D5/2 level, then this measurement corresponds to a spin projection along the Z direction. Now, when we trap more than a single ion in our traps, we use a radio frequency trap, which is a linear trap that enables us to produce anisotropic harmonic potentials. And this is what is needed if you want to create linear strings of ions. Then you need one axis which has a very weak confinement. And if you have a ratio of oscillation frequencies of the weak to the strong axis between maybe 15 and 30, then this enables us to create strings containing up to 50 ions. Now, we can measure these strings, as already mentioned, by recording the fluorescence of the ions in a spatially resolved manner by imaging it on a CCD camera. And this is, for example, what we get if we have a 15-ion string. All of the ions are in the fluorescing state. And now we can start, for example, here initializing them in this level by optical pumping and by laser cooling in order to control also the emotional state in the right way. And then we have the second important tool, which is a laser beam, which is strongly focused such that it interacts only with a single ion. And this laser beam is steerable and enables coherent single spin manipulation. So what we can do, for example, is to promote just a single ion into this metastable state. If you then carry out a fluorescence detection, you see that there seems to be one ion missing because it does not fluoresce. Of course, it is still there because otherwise the other ions would change their positions because of the imbalance of forces that would result from a missing ion. And by moving this beam around, we can make use of it, for example, to prepare some input states in a qubit resolved manner in a fairly short time. So the time to move the beam from one ion to the next is in the order of just maybe 10 microseconds. This beam is interesting not only for single qubit manipulation for input state preparation, but also for the purpose of carrying out measurements. What you have seen so far, these fluorescence measurements were measurements where we measured all the ions along the same direction, the Z direction, which is our measurement basis that is available to us by fluorescence measurements. But imagine now that we would like to measure one ion along the X direction. And that's something we could do by carrying out a single qubit manipulation that rotates the basis vectors onto which we want to project using a pi/2 laser pulse into the basis in which we can carry out the fluorescence measurement. And doing this on different ions, we have the possibility to carry out basically any measurement of any spin correlation that we are interested in the system, which is quite a powerful tool and which enables us also to carry out, for example, quantum state tomography if the number of ions is not too big. Now, so far I talked about manipulating individual ions in such a string, but now I want to discuss the important topic of how we can turn our system into an interacting many-body system. And what I want to show you is how to engineer a Hamiltonian that looks like a Hamiltonian describing a system of spins that interact with each other via magnetic interactions. So what you have here is an Ising model where you have a a coupling between spins I and J with a coupling matrix J and J, and there might be, in addition, a transverse field that is transverse to the direction in which the spin operators couple the ions with each other. And what we are mostly interested in is the creation of such a model where we have some interactions which are antiferromagnetic and where the transverse field is quite big compared to this spin-spin coupling matrix. And as a result of this, you can then induce some dynamics, which is just here pictured in the background, where you can prepare an ion, maybe flip the central spin, and then as you switch on the interaction, and as a result, when you measure the magnetization, you see that the complex pattern of magnetization arises as a function of time if you vary the duration of this laser pulse. And I want to now explain how we can engineer such an effective Hamiltonian that looks like an Ising Hamiltonian with a transverse magnetic field. And so for this, you have to keep in mind that the only interaction that we have between the ions in the absence of laser light is just the Coulomb interaction, which gives rise to repulsion between the ions and which defines then the equilibrium positions of the ions in the string. And secondly, it also gives rise to collective modes of ion motion. So if one ion moves a little bit, the other ions have to move as well. And this means that we can describe the ion motion of a string of ions by a set of collective modes of motion that describe the motion along the direction of the string. And then there are further collective modes that describe the motion of the ions in the direction perpendicular to the axis of the string. And in the limit of small excitations, this is a set of harmonic oscillators that then describes the motion of the ions. And what we can do is we can make use of this Coulomb interaction, which is long range, which couples the ions, but not in a state-dependent way, in conjunction with laser light that is able to carry out operations that depend on the internal state of the ion. So you can, and in this way, we are able then to realize interaction which looks like an effective spin-spin interaction of variable range. And in order to understand why this is possible, maybe you can think of the state dependence of the laser interaction by seeing that if an ion absorbs a photon from a laser beam, then it will receive a momentum kick. But the question is it pushed by the laser beam in the same direction? This is what happens if the ion absorbs the photon, or is it pushed in the opposite direction if it's in the upper state, and instead of absorbing the photon, there's a stimulated emission event. And this is basically the state-dependent force that we can make use of in order to couple ions in an interesting way. And here, this is how it works. So let's just focus on a very simple situation where we consider just a single ion with its state spin down and spin up, and there's a single harmonic oscillator describing the ion motion with Fock state 0, 1, and so on. We can now decide to tune the laser that couples the electronic states such that the laser is exactly in resonance with the qubit transition frequency. In this case, we just manipulate the qubit without affecting the motional state of the ions. And this is what we call a carrier transition. But there are more possibilities. So if you scan, for example, the laser frequency over the qubit transition frequency and measure the probability of exciting the ion to the upper state, then you see that this carrier transition is accompanied by what is called a red sideband and a blue sideband, which occur at a frequency spacing which just matches the oscillation frequency of the ions in the trap. And now what we can do is we can tune the laser to either this red sideband or to the blue sideband, or even to both of them simultaneously. And then what happens is the following. You have a transition where the ion, upon being promoted to the upper state, either reduces its motional quantum number by 1 unit, or it increases its motional quantum number by 1 unit. You can see that we can now describe this interaction by a Hamiltonian that is comprised of a spin flip operator sigma z multiplied with a sum of an annihilation operator and a creation operator, depending on whether you have a red sideband absorption or a blue sideband absorption. And it is this bichromatic excitation that is the basis for creating entanglement in many ion trap experiments. So the first to suggest this scheme were Anders Sørensen and Klaus Møllmer nearly 20 years ago. where they suggested to couple two ions to a joint harmonic oscillator using a bichromatic interaction that is slightly off-resonant with this harmonic oscillator. And what is going on is following. Now, with 2 qubits, we have to consider 4 electronic states, which are sketched here in this diagram, in conjunction with the motional state of the harmonic oscillator. And if you start, for example, in the spin-down state, then you see that by using this bichromatic laser field tuned in such a way that the sum of the 2 laser frequencies just matches twice the qubit transition frequency, that you get a kind of 2-ion, 2-photon transition, which couples the spin-down state to the spin-up state without a change of the motional quantum number, by a coupling that is off-resonantly mediated by a process that in between increases or decreases the vibrational quantum number by 1 unit. And if you carry out the math, and so, for example, if you just do a second-order perturbation theory, what you will find then is that you can describe this process by an effective spin-spin interaction that couples the spin-down to the spin-up state. And there is a similar process, which I did not sketch here, which couples the spin-up state to the spin-up state, either via an absorption of a blue sideband photon followed by a stimulated emission of a blue sideband photon, or by first having a stimulated emission of a red sideband photon followed by an absorption of a blue sideband photon. So it means that whenever one ion flips its state, a second ion has to do the same. And so if this is a coherent process, then it means that we can now couple these 2 levels. If the coupling is not too strong, there's hardly any population in these intermediate states. And it means that we can carry out, for example, a pi/2 pulse in this now composite 2-level system, which creates entanglement by mapping the spin-down state to spin-down plus spin-up. So then this is a way of creating a belt state. And we describe this Hamiltonian that describes the interaction that we have here between the electronic degrees of freedom by an effective Hamiltonian, which with a coupling that is given by the product of these 2 Pauli matrices for ion number 1 and ion number 2. And this is possible because the coupling strength on this transition here, coupling spin-down to spin-up, is the same as the coupling the other 2 qubit states to each other. Now, that's the basis of many gate operations. And what I want to show you now is the generalization that you get when you apply this interaction now to many ions at once, and in a situation where there is more than a single harmonic oscillator mediating the coupling. And this is how it works. So what we are now interested in is to couple the ions by making use of the transverse modes of motion of the ion string. So the ion string has a couple of vibrational modes, as many as there are ions, for example, if you describe the motion in one direction. And the highest frequency mode is the center of mass mode of ions, where all the ions move in sync. And then there's a mode which is slightly lower, which describes the tilt mode of the ion crystal. And then there are lower frequency modes, which describe modes where the ion crystal undergoes some bending operation. And then there are shorter and shorter wavelengths that are involved, which at lower frequencies. If the potential is sufficiently anisotropic, in that case, the ion crystal, the modes of these, describing the transverse motion of motion bunch in frequency space and occur over a fairly narrow range of oscillation frequencies. And so this is what you see experimentally here. We have the blue sidebands and the red sidebands of an 18 ion crystal. And what we can now do is we can make use of a bichromatic light field as before and choose a detuning that is off resonant with all of these modes, but in such a way that it off resonantly couples to these modes, and not only to a single mode, but to all of them to some degree. And by playing around with the detuning that we have and with the width of this cluster of frequencies, we have a way of tuning the resulting interaction. And it turns out that what you get are the very same basic processes. You have a coupling where ions in spin down are promoted in such a way that one ion flips its spin and one motional mode increases its quantum number from 0 to 1. I should mention that we cool these modes to the ground state because this improves the quality of the interaction. And then when a second photon interacts with a second ion, then the motional mode returns to its original state, and the second ion flips the state as well. And then once again, we have these two processes where we have either spins being coupled starting from the same state or starting in different states. And then what we get is a Hamiltonian that is described by a coupling matrix here, and then by the spin flip operators that now apply to ion A, I, and ion J. And what I should mention maybe at this point here, something is that I forgot to put on a different slide. We have one more knob that we can play with. And so I told you that we have this bichromatic interaction that we can choose such that the sum of the two frequencies matches just twice the transition frequency. But we can also detune both of the lasers in the same direction by a little bit. And this will then make this first transition off resonant. So we can suppress then this first transition here without affecting the second transition, because these are energy levels which have the same energy. And then by a change of the laser frequency, we just modify the coupling to the intermediate state a little bit without affecting the overall coupling that still exists. And this is important because you see that in this case, this Ising Hamiltonian turns into what people call it maybe XY Hamiltonian, where you have just these flip-flop processes where you have one excitation that gets de-excited, and at the same time another excitation shows up in the string. So the total number of excitation in this case is conserved if this transverse field that we engineer in addition to this Ising interaction has a strength which is bigger than the spin-spin coupling matrix. Now, what does the spin-spin coupling matrix look like? And for this, we can calculate the coupling strength in second-order perturbation theory, and we obtain a formula which is fairly easy to understand. What is important here is there's a sum where the index m runs over all vibrational modes that participate in the coupling. And secondly, there are these constants BIM and BJM, which tell you how much the ion I, for example, participates in the mode that is indexed by the mode number m. So if you have, for example, if you have the center of mass mode of motion, and this is what is sketched here on the left, this left diagram here, then all ions move in sync with the same amplitude. In this case, all these numbers are the same. And then in addition, you have here basically the tuning between the laser and the mode frequency, which determines how strong the contribution of this particular mode to the coupling strength is. We have to sum over all modes. You see, if there's just the center of mass mode, then we have a spin-spin coupling matrix as sketched here, which is completely homogeneous. So all the spins couple to all other spins with the same coupling strength, and we have some antiferromagnetic coupling because here the denominator is positive. And now I can also add the contribution of the next vibrational mode of motion, which is this tilt mode of motion. In that case, it becomes more interesting because now you see that ions which are close by, they move in sync. And therefore, this coupling reinforces the coupling that we have from the center of mass mode of motion. But ions which are at the opposite end of the string, they move out of sync. And therefore, we have here a sign change with respect to the contribution of the center of mass mode of motion. And therefore, you get a partial cancellation of these couplings. And the sum of these two, for example, produces then this spin-spin coupling matrix, which for ions close together is antiferromagnetic, and for ions far apart is slightly ferromagnetic. And then you can keep adding more and more contributions from the other vibrational modes that contribute to this example where you have 11 ions. You see in the end, we end up with a coupling matrix, which is more or less homogeneous across the ion string and which falls off with distance. And if you model this, then you can see that to a good approximation, you can describe this coupling matrix by a power law in such a way that that you have some exponent alpha, which describes how the coupling between ions decreases with the distance between the ions in the string. And this exponent can be tuned between 0, which would be the all-to-all case, and between an exponent of 3, which is difficult to achieve because in that case the coupling vanishes and goes to 0. But in between we have some room, and we can achieve exponents which might be somewhere between maybe 0.5 and 2, and which give rise to different types of physics. Now, that's something we started exploring a couple of years ago. What you can see here, if you just look at the plot on the left-hand side, is the magnetization dynamics. So time flows upwards in this case, of a string of 15 ions where we flipped the center spin. So the spin, the color encodes the magnetization that we see. The magnetization is conserved. And you see that this initially localized excitation now couples to neighboring ion and starts to spread out. There's some interference going on. And we get now a pattern of magnetization which depends on the range of the interaction that we have. So here in the left-hand plot, the exponent is fairly long range, alpha equals to 1.4. And then if we make it even longer range, as in the middle and the right-hand plot, you see that some of the excitation spreads out faster, for example, here in the rightmost plot, but at the same time, the central excitation stays localized also for a longer time. So you have a fairly complex dynamics that is going on. On the other hand, it's still quite simple to calculate what is going on, because what we have here is a single excitation. And I told you in this limit of a strong transverse field, this excitation can reside in one of the 15 sites that we have. And so we do not have a very big Hilbert space that is available to this system starting in this initial state. We have just an n-dimensional Hilbert space if we have a single excitation in a string of n ions. And so it's very easy to calculate what we should expect to see in the experiment, which is good because in this way we can experimentally check how well the experiment really works. It's bad in view of trying to build a quantum simulator which is supposed to be maybe able to do a calculation which is difficult on a classical computer. But there's a way around, and the way around is to make the initial state more complex. If, for example, we do the very same experiment, but this time we prepare here a 20 ion string in a near ordered state, that is, initially we flip every second ion to the up state and then switch on the dynamics, you see that here the excitations start hopping from the even to the odd sides, and in between you could expect probably the excitations to be delocalized, and so you would expect to have entanglement in the system. But then over time the magnetization seems to settle to some value which is around 0. And now the question is, what is it that we are seeing here in our experiment? Is this now a highly entangled state where the excitations are completely delocalized over our system, or is it just a noisy mess because we do not control decoherence by coupling to an environment which we always have in our experiment? And so the question then is, how can we characterize entangled state if we have more than 8 ions? So 8 ions is the biggest number that we ever investigated by brute force quantum state tomography. Or we could ask how coherent is the engineered spin-spin interaction in our experiments. And so these are questions which tell us that a characterization of the resulting state that we expect to be highly entangled is an important part of our experiments. And we have done a couple of different experiments along these lines. For example, we looked at quantum state tomography of subsystems, and then that's something which you can use for checking that at least in the initial stages of the dynamics, everything looks fine, and you have maybe multi-part entanglement over a couple of spins. We have looked at matrix product state tomography. So that's this case, we assume that our system is maybe we hope that our system is close to a pure quantum state, and we make use of the fact that we have interactions which on the one hand side are long range, but still, I mean, it's mostly neighboring ions which are close together, which interact strongly with each other. And so we can hope that in the initial stages of the dynamics, only maybe groups of ions which are close by become entangled. And then it might be a good way to represent the state by a matrix product state. And then there are techniques for reconstructing the state using a limited set of correlation measurements, and then you can do further measurements in order to check how close your experimental state might be to the reconstructed matrix product state. So that's something which is good if you want to check the initial dynamics, and then you have maybe some tools that are scalable in the number of ions. More recently, we did something which is on the opposite end, that is a technique that is not scalable, but still better than tomography, but which does not make any assumptions about the nature of the states that we produce in our experiment. And this is an entropy measurement by making use of random unitaries. And in this way, you can look at the entropy of either the entire system or of subsystems, and this gives you access to questions like a measurement of the purity or a measurement of maybe entanglement generated by non-equilibrium quantum dynamics. So measuring the purity is important for us from an experimental point of view because we know that we have decoherence in our experiments, and so it would be nice if we could just measure the trace of rho squared in order to find out maybe how close to unitary the quantum dynamics is that generates states. And measuring the entropy of subsystems is an interesting tool if the dynamics itself is sufficiently close to unitary, because then by measuring this entropy, it tells you that the entropy must be the result of quantum correlations between the subsystem and the rest of your system. The problem only is that now purity and entropy depend in a nonlinear way on the density matrix, and so there's no observable that you can easily measure in our system. And for this reason, we made use of a proposal which was first made in the context of quantum computing, and that is to produce something like two virtual copies of our quantum system. And it turns out that if you have a density matrix that you have available in your lab, and you carry out some set of random unitary operations, U alpha, and then carry out a measurement of some observable, and you average over these random unitaries that you have chosen with the right amount of randomness, then you get access to the purity. And in a way, what you do is when you have, for example, the purity, then you know that you have products of density matrix elements that enter, and by choosing the right unitaries, you can, in this expression, eliminate those entries which you don't want to have, and such you're left only with the ones that you want to know. And I can't really go into the details here. What I want to mention is that this is an experiment which was done in collaboration with the theory group by Peter Zoller in Innsbruck, and who had adapted the scheme to a quantum simulation context. And after discussions with them, we settled on trying to use a scheme where we have something like local quenches. That is, we time evolve our quantum state, and then we carry out a set of random unitary operations, which you can see here on single qubits, and carry out a measurement. We do this, we repeat this experiment a certain number of times in order to get the required statistics that we are interested in. Then we switch to another set of random measurements and do this multiple times. And in the end, we average over these results, and then we get access by these measurements to both the total purity of our system or also the purity of all subsystems the system is composed of. And what you can see here, what is plotted on the left plot here, is now a measurement of the purity of subsystems. And maybe let's first focus on the upper line here, which is what we measure when we prepare the ions initially in this Néel-ordered state where every second ion is a spin-up state. In that case, we have a product state, and so hopefully the purity should be 1. We see that if you have 10 ions, the purity is not entirely 1. This is partially due to errors in the state preparation, partially due to errors when carrying out these random unitaries. And that's something I think we understand fairly well. What you also see is that then the purity of subsystems is higher than the purity of the entire system. And the more ions you're looking at, the more the total purity is reduced, which is not really surprising. Now, switching on now the entangling interaction, you see that the purity of the total system hardly changes at all. And this is good because it tells us that the entangling interaction does not seem to introduce a lot of decoherence on the time scale of the experiment that we have looked at here. On the other hand, the time scales are such that the purity of a single qubit, for example, drops dramatically within a very short time and becomes completely mixed. The same goes for the purity of pairs of neighboring qubits that you can see here, which also become nearly completely mixed. And also, if you look at the half-chain entropy, then you see, now this is the purity. If you can easily convert this now to a Rayleigh entropy, you see that the half-chain entropy here becomes very high. At the same time, the entropy of the entire system stays low. And this tells us that most of this increase of entropy that we see here when we just look at the half-chain entropy has to be due to correlations building up with one half of the system and the other half of the system. Now, this is now a good tool for us to look at quantum dynamics that we could not easily investigate by other means. And we have used this in a different experiment that I want to sketch now, which is very different, where we use now here entangling interactions as a resource for variational quantum simulation. In the next slides, I want to explain to you how this works and what we have been doing. So imagine that you have some Hamiltonian, which is maybe the sum of Hamiltonians which involve only a finite number of qubits or spins that you would like to investigate. For example, you would like to know what is the ground state of this Hamiltonian, what is the ground state energy. On the other, but it's not possible maybe to realize this Hamiltonian in the lab directly with interactions that we have available in our experiment. On the other hand, our experiment can be seen as a quantum resource because we have these entangling interactions that I just described to you, where we have these flip-flop processes with the spin-spin coupling matrix, where there is some control over the exponent here, alpha, and where we can induce now some entangling operations of a variable duration by controlling the duration of the laser pulse. And then in addition, we have these single qubit operations, and then we can make use of our elementary operations to build up some unitary by applying different operations one after the other. And in this case, this way, we can then create a family of entangled states that is described by some parameter theta, which is a vector which is comprised of all these rotation angles that show up here. And the question is, can we make use of this quantum resource in conjunction with some classical computation in order to learn something about a Hamiltonian that we cannot directly realize in our lab? And the way to do this in variational quantum simulation is sketched here. So imagine that we want to prepare now the ground state of such a Hamiltonian by minimizing the energy of by finding the minimum energy of the Hamiltonian with respect to this family of states that we can produce in the lab. We cannot produce a Hamiltonian, but we can produce the states that we're interested in. And so what we do is we have maybe our control computer tell our experiment to produce one of these states here. And then we carry out quantum measurements after having produced the state in order to measure some observables that are interesting. And which are the ones that are interesting? Imagine you have this target Hamiltonian, which is, as I mentioned, a sum of different terms here. And maybe you cannot realize this Hamiltonian here in the lab, but what you can do is you can maybe realize the measurement of an expectation value of the observable described by H1 with respect to the quantum state that we have here, which in this case could be a spin correlation function. And so in order to do this, imagine that we have now maybe one term here that is comprised of a measurement of the spin correlation between the spin 3 and spin 5 in the x direction, and then there's a certain weight given to the Hamiltonian, in the Hamiltonian. And so we repeatedly measure now our ions 3 and 5, and we correlate them, and we get, of course, different results. And in the end, when we do this, we can estimate the expectation value of this term, and then we can multiply it with this constant here, and then proceed to a measurement of the next term in the Hamiltonian by the same way. And in the end, we sum up these expectation values, and then this should be an estimate of the expectation value of this particular quantum state with respect to this target Hamiltonian. And having done this, having now an estimate of this energy, the computer can now suggest a new quantum state in order to see whether it has a lower value or a higher one. And by changing then these the rotation angles that we have. And just to mention, we have these entangling operations, we have these single qubit operations, we have collective qubit operations. And in the experiments that I show you here, we had up to 20 ions. We used up to 6 layers of these operations. And in this way, we had 15 different variational parameters that we tried to optimize. And this is what we got. So you can see here the estimated energy as a function of the iteration of this repetitive scheme. And you see that these measured energies are all over the place, but there's a general tendency to go down. So if you collect all the information that is available and you try to estimate to have the best estimate of the measured energy, you see something which goes down and which comes pretty close to the known energy of the Hamiltonian that we had been looking at in this experiment, and which is much closer to this energy than the energy gap between the ground state and the first excited state. That's maybe an important quantity here to know. And what we also see is that, well, we can measure the energy, but of course we can also, since here we have a simple model problem, just simulate the experiment, and then we have some simulated energy that we expect to see. And we have a pretty good match between the measured energy and the simulated energy. So that's fine. And also when we do this, we can also, for a given set of parameters, we can calculate the expected overlap between the true ground state and the state that we hope to prepare in the experiment. And in the course of this optimization, this overlap went up to 80%, which means that we had a sufficient number of resources to prepare a state which is fairly close to the ground state of the target Hamiltonian. And so something like 84%. Now, so far for variational quantum simulation. Now I want to talk about options for scaling up our experiment to a larger number of ions or qubits. And there are basically 2 ways of doing this. One is to make
Christian.
Yes.
Christian, sorry. More or less like 8 minutes would be okay for you?
That should be okay. Yeah. Okay.
More or less. Flexible.
Yeah. Let's see. You interrupt me if you should think that I go over.
We're happy to hear you talking more and more. Go on,
So we can use either longer strings, or we could try to think of using maybe 2-dimensional ion crystals. And I first want to discuss the longer string option. And so until recently, we had 20 fully controlled ions in the sense that we could carry out single qubit operations on a set of 20 ions. In the last 2 years, we extended this capability, and now we are able to address up to 50 ions in a string. This is what you can see here. So here you see that every peak corresponds to a different ion being excited by this focused laser beam that is scanned over the ion crystal. And you can see that for an individual ion, you can drive Rabi oscillations and in a context where the neighboring ions have interactions which are much, much weaker. And so we can now carry out the same experiments I showed you with smaller number of ions. So here you see a 51 ion string where we flip the central ion. You see that the excitation starts to spread out in a pattern that matches pretty much what you would expect from a simulation. And by now, I think we also have better data than the one that I show you here. And we can also repeat these experiments where we flip many ions to prepare a nil state. And then once again, you see that we have this pattern of excited spins, or spin excitations, which starts to hop around, probably become entangled. And then after a while, this pattern washes out if you just look at individual ions. And what we see here is also an experiment pretty close to what we expect in theory. And if you carry out quantum state tomography, for example, between pairs of neighboring ions, you see that initially here, roughly at this time here, you see that every ion becomes entangled with its neighbor. So we have clearly complex entangled states present in our experiment. More recently, I want to briefly mention an experiment that we are about to finish now, What I described so far were just measurements of quantum correlations by looking at the propagation of single or multiple excitations. And in the case of a single propagating excitation is fairly, fairly non-typical in the sense that this is the number of possible initial states is that has just a single excitation exponentially small in the number of initial states. If you look at product states, for example, you could start with. And so what we became interested in is to look at the transport of some conserved properties, like for example, the total magnetization is conserved over time and space in these systems here. And so instead of looking, for example, at 2-point correlation functions where you correlate spins at the same time, you could also wonder, is it possible to learn something about the transport if you look at 2-point correlation functions when you start out with some initial state where you have some localized excitation, and you try to follow this localized excitation to different sites and look at the correlation that you get when you look at later times. And here you could, when you think about these long interactions that we have, you could think that we have maybe some hopping excitations, and maybe sometimes we have just short jumps, which are quite frequent. And sometimes we have the long range excitation, we have long jumps. And so the question is, what kind of dynamics do we get? Maybe we have something like Levy flights that are present here that could matter. And in collaboration with the theory group led by Michael Knapp, who published this paper here about this particular problem last year, we have done experiments where we try to create now a single excitation on top of a highly excited state, such that the single excitation interacts with other excitations, but in a way where we can still trace now this imbalance of magnetization that we have in our string. This is different from this context that we have here, where every second ion is flipped and where we don't have any easy way to look at a transport experiments. And what our theory collaborators have seen is that depending on the range of interactions, you get dynamics that can be described for some of these exponents by some hydrodynamic transport, where when you look at the autocorrelation function, you see that this magnetization that you have initially falls off with some tail that is linked to the exponent that you have, and that is something we recently looked at in an experimental way by making use of our ability to prepare particular input states. And what we have done is to prepare a state which has a total magnetization which is nearly zero. So it means that what we have done is we have the central ion in long string we prepared in a definite state where we had one spin excitation, but all the other ions were equally likely to be in the up and the down state, but with the boundary condition that the sum of excitations in the other states average to zero. And then what you can do is you can then estimate these 2-point correlation functions for the case of an infinite temperature by basically averaging over many different realizations of these input states. And what you see is that you get a fast equilibration locally that happens, followed by then a long tail where these correlations that you get then decreases. And what you see that it's a bit difficult now in the experimental system now to really extract some exponents here for this decay, which depends on the range of the interaction, because we have access to this dynamics over a limited scale of time scale here. But still, we see that we have some differences in this tail depending on the range of our interaction. And with our system, we also have access to to spatially resolve this process here. And you see here that if we have this long range exponent, we see that initially this localized excitation starts to spread out and to decay, and then you get a profile which is expected to be roughly Lorentzian. And if you compare the data, then you see that indeed we have a fit which is better with a Lorentzian than with a Gaussian function. Whereas if you go to longer range excitations, you see that the Gaussian fit starts to become better than the Lorentzian one. So for alpha equals 2, one would expect to see a Gaussian profile, whereas here we are somewhere in the intermediate regime, but we see that, we have these signatures of this transport in the spatial dynamics as well. Now, my last topic before I conclude is to talk about the other option. So why do we not go on only with just 1D ion crystals? The problem is we can make ion crystals longer and longer, but in order to keep them linear, you have to relax the axial potential more and more. And this goes basically in proportion to the number of the ions you want to keep in your linear crystal. And so you have very low axial confinement, which makes it hard to control the axial mode of motion. And also the ion strings become very long. And the question is, how long can we make them? Maybe you can go to 100, I don't know. But it's certainly worthwhile to think about alternatives. And one alternative is to make use of 2D crystals. And there are basically 3 approaches to having 2D ion crystals. One is using panning traps. One is making use of micro-trapped arrays where each ion is trapped in each individual radio frequency trap, or to use a kind of standard linear radio frequency trap. And all of them are problematic. So panning traps are difficult because these ion crystals tend to rotate fairly rapidly, which makes single ion addressing a big challenge, and also measuring the ions one by one in a spatially resolved manner. Microtraps are difficult because you need to bring ions very close to the trap surfaces, and then you get electric field noise that is somehow living on these trap surfaces. And RF traps are not easy because then you have ions sitting at locations where they feel this strong driven motion, radio frequency motion of the ion trap. And this is the option that we have chosen in a new experiment. And so the idea is to produce something like a planar crystal, where you have once again the out-of-plane modes, which replace the transverse modes of motion of a linear string and could be used to mediate entanglement. And the idea is to use a laser configuration, which is sketched here, such that the lasers couple to a crystal in a way so that the laser interaction is not affected by the driven radio frequency motion the ions experience in the radio frequency trap. And so then it should be possible to have a coherent coupling to these transverse modes of motion. And it should also be possible to laser cool other motional modes, for example, the in-plane motion on the crystal, at least in a way that this is not affected by macromotion too strongly. And so where are we? We have designed a new monolithic ion trap, which is sketched here, which enables us to trap planar crystals that you can see here. And this works so far pretty well. We have ground state cooled a single ion using cooling by electromagnetically induced transparency. And we believe that cooling of these 2D ion crystals should be straightforward for the collective modes of motion. That's actually something we hope to prove this week. And then the next step would be to set up the spin-spin interactions in order to interact with these crystals the same way as we have done with the linear strings. And with that, I'm at the end of my talk, so I hope that you got an idea of how we can realize these long-range Ising models in trapped ions. We have now strings of 50 ions that can be addressed and where we can measure arbitrary spin correlations using single-shot measurements and create entanglement in 50 ion strings and characterize this entanglement in subsystems. And you have seen that we have started doing first experiments to explore interesting quantum dynamics in these long-range quantum spin systems where you have really many spins and where calculation of the dynamics starts to become a problem if you just want to use classical techniques. And as an outlook, I mean, of course, we hope to continue to go on. We're working with these non-equilibrium quantum dynamics systems with more than 50 spin ion qubits in a linear string. And in addition, we hope to go to planar ion crystals and carry out similar experiments. Thank you.
Thank you very much, Chris, for the excellent talk. This has been a wonderful explanation of many different topics, and congratulations for the results. These experiments are amazing. We have some minutes for some questions, and I will start by a question that is written here. Anonymous attendee, so this is somebody not registered, but the question is the following. So it's about the first part where you talk about the linear range. So are the ions at the extreme ends of the string also only held to the rest of the string by Coulomb forces, or is there another force needed to keep ends of the chain in place?
Well, there are two kinds of forces that we need to consider. So one is the confinement of the ions by the trapping potential. So we have, I did not try to describe this in detail. We make use of radio frequency fields that interact with these charged ions. And the radio frequency fields are designed in such a way that we create some effective force if you average over the fast dynamics of the radio frequency field that looks as if the ion was trapped in a harmonic potential. Mm-hmm. And if you place now more than a single ion into this potential, then you have an equilibrium of forces, which is given on the one hand side by the confining forces of the ion trap and by the mutual Coulomb repulsion between ions, which then decides the locations where this ion string or ion crystal is able to minimize its energy in this configuration.
I see. I also had a question myself connected also to the coupling between the ions. So when you were showing in the beginning how to realize the Ising model in a linear configuration, so one of the restrictions that I think you mentioned is that the coupling between you have this power law for the couplings between the different ions, but you also mentioned that if you consider a transverse field Ising model, then the interactions that you guys can attain is always smaller than the transverse field. What is the origin of that? Because that limits your range of possible applications in terms of quantum simulations, right?
Yeah. Let me answer your question. Maybe I just switch to the next slide to acknowledge that okay. This work, which I did not only myself, but also that there are quite a number of other people that are involved. I mentioned that the experiment that I presented to you are done in this regime where the transverse field is quite a bit stronger than this spin-spin interaction. Now that is a deliberate choice that we made. So if we want to, we can work in the regime where we have really an Ising model with zero transverse magnetic field.
Oh, I see.
But actually, it is quite nice to have this fairly strong transverse field, because in this way you can carry out experiments in a subspace that is decoherence-free with respect to the dominant mechanism of decoherence that we have. So imagine that you prepare an initial state with a given total magnetization, and you have this transverse field Ising model. Then I told you the total magnetization is conserved. And this means that now what are the major sources of decoherence? On the one hand side, we have a laser which is extremely frequency stable because we couple now two energy levels which are separated by an energy that about 2 electron volt, which corresponds to a transition frequency of 4 times 10 to the 14 hertz. And now, if now these energy levels fluctuate with respect to each other, then we get a dephasing. And similarly, if the laser frequency that we have is not perfectly stable, then we get also a dephasing of our qubits, because whenever we talk about the phase of 2 qubit levels, we have to do it with reference to a rotating frame rotating at the laser frequency. And if this rotation is not perfectly constant, then our measurements will look as if the ions had decohered. And so you see that dephasing is our main source of decoherence that we have. If we now work in a regime where the transverse field is much stronger than the spin-spin interaction, we suppress these joint spin flips where 2 ions flip and become excited, and then the states with a fixed magnetization have exhibit all common mode fluctuations with respect to these sources of decoherence that I just described. And so the relative phase is not affected between them. And for this reason, in this subspace, we have long coherence times.
I see. Okay.
I mean, we're trying to make the magnetic field as stable as possible. We're trying to improve the laser coherence. But whenever we leave the subspace, we have shorter coherence times. And so for the moment, I think it's nice to work in this subspace.
Right. And this is also the approach that you will pursue for the 2D crystals also, right? You will also stay in that regime. So
for the 2D crystal, I should mention then we think of making use of a slightly different qubit, that is to make use of two ground states and then two Zeeman states to encode a qubit in, and that should relax the requirement with respect to the laser frequency stability. You still have the magnetic field that can fluctuate.
Okay, okay. We have another question here from Lakshmi. Thank you for the wonderful presentation. Question, other than simulating magnetism Ising model, what other kind of quantum simulation have been or can be done in the future?
Yeah. So for the moment being, I would say we have this possibility of engineering some spin interactions, which always are long range in these ion trap systems. There might be the prospect of engineering additional terms. Maybe it's possible to have something like a Heisenberg model, or to have some ZZ term in addition to the XX term that I described to you. So that's something that might become possible in the future. I mean, given that we do not try to build a quantum computer in this system here, we have some limitations as to what we can simulate with interactions in our lab. And the big advantage is that it's much easier to go to a large number of qubits in this way if you have some interactions that arise naturally. But of course, this gives rise to some limitations. On the other hand, maybe this technique of variational quantum simulation might enable us also to look at other problems which are not described by this type of entanglement.
Right. Thanks for the answer. Since you touch upon that point, so in the variational quantum simulation, so you showed like that you mentioned that you can apply up to 6 layers of gates of this parameterized circuit. Yes. And so you were showing experiments for 20 ions, right?
Yes.
And there you use Mellmer-Sorensen couplings between the 20 ions at the same time, right? So you apply like this 20 qubit entangling gates, right?
Yes.
So this is something unique to this platform, essentially. Like I have seen variational quantum eigensolvers on circuit-based models, and typically you have a connectivity restriction.
Yeah, that's
whereas
right.
here you can explore that possibility, which is very, very interesting.
Yes, yeah.
Right. So more congratulations. There's Amro. Thank you for the wonderful presentation, Professor Christian. Very elegant physics. Okay. So I think that with that last compliment, it's a good time to close this session. So I don't know. This has been wonderful having you here again, Christian. Thank you so much for the amazing physics that you guys are doing in Innsbruck. You're really leading something very, very powerful for everybody in our community. And I want to thank you again for your time, for being here, and for explaining to us very careful the series of experiments that you've been doing over so many years. So thank you so much for that. And hopefully we'll have the chance to see you here physically at some point when it becomes easier to travel, right? So
yeah, yes.
Okay. Well, so thank you all guys for being here. Let's finish the session here, and we resume next week with the next edition. All right. So thank you all again. Bye bye. Have a good afternoon.
Bye bye.
Bye bye.
Okay. Thank you. Thank you very much, Christian. Really.